we were discussing the information coming from direct measurements of neutrino masses, C13 squared, C12 squared, M1 squared, plus C13 squared, C squared, 1, 2, M2 squared, plus 3 squared, M2 squared, square root of this is M beta. M beta beta is modulus C13 squared, C12 squared, M1 plus C13 squared, S12 squared, M2 e to the I phi 2 plus S13 M3 e to the I phi, let's say phi 1, phi 2, or phi 2 and phi 3 in some notation, but it is not important. So we have something depending on the neutrino mass spectrum. Remember that this is normal ordering, and this is inverted ordering, that this is the large delta m squared, and this is the small or the solar delta m squared. And the small delta m squared is always positive, while you go from normal to inverted ordering by changing the sign. So assume that this is positive and inverted order is minus this one. Now, if you consider that, for instance, here M2 is equal to square root of M1 squared plus delta M squared, and M3 can be also expressed as a function of the 2 delta M squared, these three observable are not independent, but they are correlated, meaning that if you, for instance, you fix a value for sigma, let's say 0.2 electron volt, the allowed values for M beta beta depend on the values that we give to sigma. Then we can derive M2 and M3 from sigma once we know the 2 delta M squared, obviously with an error. And if we put here the oscillation parameters and vary in the 0 to pi range, actually it is enough 0 pi range, the 2 Majorana phases, we have for every fixed value of sigma a certain range allowed for M beta beta, both in inverted, red, and normal ordering. Okay, so this plot represents the values that, for instance, contains the values that are 2 sigma and 3 sigma for the dots, and beta can have when you fix the value of the sum of neutrino mass. Same thing up there for M beta as a function of sigma. And you see that since you don't have this freedom given by the Majorana masses, virtually if you fix sigma, you fix M beta. And also you can consider what happens for M beta and M beta beta. You give a value to, for instance, M beta. This is an implicit equation begins an implicit equation in sigma or M1, and then you can calculate the allowed values for M beta beta if you vary the two phases. And cosmology will give bounds on the sum of neutrino masses. Neutrinoless double beta decay bounds or evidence one day on this effective M beta and beta mass. Beta decay experiment, like for instance scattering, can give information on M beta. And yesterday I told you that now the limits are a sub-EV level 0.8 at 90% confidence level, and scattering will be able to reach 0.2 in M beta. In the literature, you will find similar plots, but on the x-axis, often you will find M1. And these plots are maybe more easily interpreted, but actually M1 is not observable. It is sigma that gets bound from cosmology. Notice also that the lower value for sigma is different in the two orderings. This is because here you have only one massive, in quotes, state, and here you have two. Remember that the heavy neutrino has a mass of around about square root of delta m squared, and this is 0.05 eV. So in normal ordering, you have just one heavy state, and so the bound here is this one, around 0.05. And in inverted ordering, you have two states, and so the bound is around 0.1, okay? Also, in the case of normal ordering, M beta beta can go to 0, because you have these two complex numbers that can cancel and also cancel the first one. So if the true ordering is the normal one, maybe neutrinoless double beta decay experiments will never find a signal. Okay, this is an unlucky possibility. While if the true ordering is the inverted one, so this one, then neutrinoless double beta decay experiment could find a positive signal if neutrinos are the main contribution to the neutrinoless double beta decay. Right. Now, we want, this is only from oscillation. Here, there is no information from the direct measurement experiment. What happens if, for instance, start to consider what the information coming from cosmology? Obviously, the bounds on sigma depends on what data sets you combine. Only CMB or large-scale structure, the BAO, etc. So if you consider the lambda CDM standard cosmological model, if you consider the lensing or not, without going into the detail, if you have some bounds from cosmology, you see that the allowed region will change, and in the case of stringent bounds near 0.1 electron volt, in this case it's less than 0.2 at 2 sigma, you start to question the possibility of inverted ordering. Obviously, there are also bounds coming from neutrinoless beta decay and beta decay, but these are not competitive at present with respect to the information coming from cosmology. Okay, but they start to be so. Now, since we are starting to explore the region of small sigma here, maybe we change the scale and use the linear scale. You can do this. And also here, depending on the data that you analyze, bounds on sigma can be very stringent or still allow a large parameter space. And here you see that also bounds on m beta and beta from the current experiments start to give some upper bounds. Now, this was just to see how to combine in just one plot, essentially, all the information coming from oscillation experiments that explore this 6-dimensional parameter space, triangle, 2 delta m squared, the phase delta, and the ordering with cosmology and large-scale structure data, and direct measurement experiments. Now, future the problem with neutrinoless double beta decay is that what experiment measure is a lifetime, okay, for some nucleus germanium, xenon or molybdenum, and so on. But the theoretical matrix element is known with a large uncertainty, okay? Not percent, but even a factor of 2 or 3. And so, if you want to derive bounds on m beta beta from the measurement, you need to take into account the uncertainty on the mass, on the matrix element, and so the bound, it is not defined in an extremely precise way. But future, let's say in 10 years experiments, should start to investigate the region of the red plot here. So maybe we could have some hints about the existence of neutrinoless double beta decay that would indicate a Majorana mass for neutrinos. And hopefully also next generation for beta decay could increase the sensitivity by a factor of 10 and start to question what is called, in a not proper way, the inverted ordering region. Here, the ordering can be both inverted and normal, okay? But if we go down, you exclude the inverted ordering region. Okay, now the final plot is this one about, I told you, this is important for model building to understand the form of the neutrino spectrum. And if you combine all your information from oscillation experiments, for instance, if you take only accelerator experiments, actually Solar and Camland, I didn't talk about Camland, but Camland was a medium baseline reactor neutrino experiment. So under a mine under a mountain in a mine in Kamioka, an experiment measured reactor neutrinos coming from, let's say, from 100 to 800 kilometers away, and constrained the solar parameter theta 12 and the small delta m squared. So solar and Kamlan, they go together, always they go together, because they probe the same subspace of parameters. And the accelerator experiments, the probability wants as an input the solar parameters. But here, from long baseline accelerator, essentially from T2K and NOVA, the preferred ordering is the inverted one. But when you take the value of θ13 coming from reactor, short baseline reactor experiment, here you see this is the delta K square. The preferred ordering is actually the normal one. And when you add also the information coming from atmospheric neutrino experiments, essentially Super Kamiokande in Japan, you get this 6.5 in delta K square, so around 2.6 sigma, preference for normal ordering. But as you see, there is some, not tension, but disagreement between what accelerator neutrino experiment prefer and all the rest. Then, cosmological data are not very sensitive to the details of the spectrum, okay? Too small are the mass differences to give you some information. But nevertheless, if you take the output of the Cosmo MC analysis, etc., you see that depending on how you combine data sets, you can have also some small preference for one ordering or the other. This is here. For the last paper that our latest work, depending on various different combination of data, we get some weak preference for normal ordering. And here there is a very, very small difference, but this is coming from the current neutrinoless beta decay experiment and from Catherine. A small, very small difference. And then you can combine all together, and you see that in the standard, in quote, case, we have now a preference for normal order. So this one, at about 3 sigma. But this is not so robust that you can say, okay, this is the spectrum of neutrinos. Still, there is room for things to change with new experiments. In particular, 2 big projects are underway, under construction. One is Juno in China, and the other is Dune in the States. And upgrades of current accelerator experiments and the new generation for neutrinoless beta decay and beta decay experiment. So there is something coming in the next 10 years or so. Let's say that in a few years we could have new data and maybe confirm or let's say this or not this preference for normal oscillation. The other open question concerns CP violation. CP violation is the difference for the probability nu alpha to nu beta with respect to anti-nu alpha to anti-nu beta. This depends on delta. And still, the measurement of delta is not so precise. And the nature of neutrinos, if Dirac or Majorana, and oscillation experiments cannot tell you this, but if neutrinoless double beta decay is observed, then necessarily you know that neutrinos are Majorana particles. And this is the picture right now. So, if there are questions, if not, we change new page and we discuss briefly in the rest, in what remains supernova neutrinos. Okay? Fine. And okay, some plot, maybe it is useful to see. Now, in general, when you consider some neutrino experiment of one component of the GANs of this big grand unified neutrino flux, you have always a scheme with source, propagation, and let's say propagation and detection. Okay. Typically, oscillation are important during propagation. But in the case of supernova, also to define what the source is a bit tricky, and maybe oscillation are also important in the source. And the detector, in a certain sense, all the Earth is a detector for supernova neutrinos. So when they arrive, they can pass through the Earth, and so you have to consider also the matter effect in the Earth. So also in the detection, in a certain sense, the oscillation could be important. Now, for supernova, we know that there are two possibilities to measure supernova flux. One is the diffuse supernova flux, so the remnant of all the past explosions, and maybe with the upgrade of Super Kamiokande experiment with gadolinium, we will be able to measure this flux, or in the Hyper Kamiokande detector that will be built, and on one side. On the other side, the future, I don't know, in next years, 10 years, or tomorrow, galactic supernova explosion certainly will give, in the current experiments, thousands of events, electron, neutrino, antineutrino, and so on. So there are many experiments that will be able to measure supernova neutrinos from a galactic supernova at 10, 15 kiloparsec. We hope it is not too, is not near the Earth, actually. Now, typically, there are three phases in neutrino emission of supernova. Neutrino emission, as you saw with Professor Capozzi, let's say, transport out of the star all the binding gravitational energy. So there is a huge flux of neutrinos, and there are three phases: burst, accretion, and cooling of the stars. There are some, we started with one-dimensional models, and now we have many three-dimensional supernova explosion models, but they can describe only 1 second or so, 1.7 second, or most recent simulation. What is important is that there is a kind of hierarchy between the fluxes, so that you have more nu E than anti-nu E, and more anti-nu E than nu X, where nu X are mu and tau neutrinos. And typically there is also a hierarchy in the mean energy of the spectrum, so that nu E have lower mean energy than anti-nu E and then nu X. Okay, but this depends a lot on the model. But more or less, this is the hierarchy. These supernova neutrino are can help the explosion, at least in the simulations, because they are able to transfer energy to the shock wave when the shock wave is stalling. So in this sense, to study neutrino oscillation was important, or is important, to understand if this mechanism of energy exchange could help the supernova explosion. Some years ago, things seem to be clear, in the sense that when the neutron star is formed, after the burst that corresponds to the deleptonization of the star, there is this emission, more or less continuous, for 10, 20 seconds, and so neutrino propagate in the matter of the layers of the exploding stars. And then you have to consider the matter effect in this matter. And you cannot consider two flavor oscillations, but you have to consider three flavor oscillations. But since you have two possible resonances, one for the large delta m square and the other for the small delta m square, the fact that these two delta m square differ by a factor of 10, roughly, makes the two resonances happen at two different distances, so that the problem, in some sense, can be factorized as two generation oscillation. It is not nearly absolutely true, but more or less it's the same. And so, just as an example, instead of having only one plot, we consider, for instance, only this one, you have to consider a plot with three mass eigenstates. Then you see when a neutrino, for instance, a new E is produced, you know the density, more or less, very large density, 10 to the 12, 13 times the Avogadro's number. And so, from the, the mixing, and you can say the probability that a nu E is a nu 3 in matter, nu 2 or nu 1, essentially, for instance, is a nu 3. Then you follow this line in the case of adiabatic propagation. When the two mass eigenstates are, let's say, close, there is the probability of a jump. And so you can calculate in a relatively easy way the probability that starting from up there, you can arrive, for instance, down here. You have, for instance, the probability of jump when there is this resonance due to the one of the two delta m square, and another probability of jump here. This resonance happens typically at a distance of hundreds or thousands of kilometers. And okay, you should do the calculation numerically in the end. But through this approximate factorization between, let's say, two generation problems, you can understand well what the formula the numerical analysis tells you, okay? And this was the study from, let's say, in the early 2000s, and the problem seems to be fairly well understood. Then you start to introduce complications. For instance, fluctuations in the matter density through neutrino propagation, or turbulence. But all these effects were included in numerical analysis. And you could predict with confidence the neutrino fluxes at the surface of the supernova. Then you propagate neutrinos in the vacuum. Then, depending on the detector position, you take into account it's called MSW effect, so the matter effect that was studied by Wolfenstein, Mikhaev, and Smirnov. It's called, instead of matter effect, MSW effect in the Earth, or not, depending on the detector position, and you can predict the neutrino fluxes. In this way, you could, the problem could be seen from two different perspectives. On one side, if you imagine that your description of the supernova is accurate, you can use supernova neutrino to constrain neutrino parameters. So the mixing angles, mass differences, and also the ordering. Supernova neutrino could, in principle, give you information on the neutrino mass ordering. On the other side, maybe your description of the exploding supernova is not so good, but if you have a good measurement of neutrino spectra, you can infer information on the supernova physics. So these two perspectives are both present. How many times, Helio? How many times? 5 minutes. Okay, and this was the situation, let's say, until 15, 20 years ago. Then it was realized that, okay, before going to this, there was one supernova in 1987, okay, but the events, recorded events, 20 events, were not enough to study this problem, okay, because there were 20 events in tenths of second, and so no actual spectrum, because to get information on neutrino oscillation parameter, you need a neutrino spectrum, okay? So you need events both in energy and in time to do some good analysis. So now, from 2005 or 10, it was realized that also, besides matter effect, there is another kind of particle important for neutrino scattering, that are neutrino themselves. So neutrino scattering is also important. Since the density is so high, neutrino-neutrino interaction can trap the neutrino for a few seconds in a sphere, the neutrino sphere. And you can imagine that from this sphere, the flux is emitted for a few seconds. So, what is the effect of this neutrino-neutrino interaction? The effect was very, very interesting, unexpected, as all beautiful things. Also, sometimes unexpected things are not so beautiful, but we will discuss that after a coffee that you need more than me, probably. Okay? So in 10 minutes or so. okay? And as I was telling you, was asked me, today I will give my note to Elio, and you will find. And maybe there are some typo. I was trying to find all the typos, but still there are. And now, as I was saying, it was realized that neutrino self-interactions are very important, and to study these self-interactions, the appropriate formalism is the one of the density matrix, okay? And let's consider, for instance, two flavors only, but actually this can be generalized to three flavors. And in this case, these are nu E, nu X star, nu E star, nu X, and nu X square. And essentially, these are occupation numbers. When you have diagonal form, no oscillation, the off-diagonal terms in the density matrix corresponds to oscillations. And the equation of motion for the density matrix is rho, let's say P R T plus V P gradient with respect to R, rho P R T equal to minus I omega, that is a function P R T rho, where this omega is the sum of three terms, vacuum plus matter, MSW, plus, let's say, self-interaction, and omega vacuum is 1 over 2e u m diagonal u dagger. MSW term is square root of 2 GF N E R diagonal 1 0, actually in two flavor, only this one, and the new term is square root of 2 GF D3Q 2 pi cube rho P R T minus rho Q R T times 1 minus V Q dot V P. Okay. Now, for instance, if you have a stationary situation, the first term in the equation of motion is 0, while if you have an isotropic distribution for neutrino, it is the second, it is 0, and the equation for the density matrix is equivalent, in the end, to the equation for the neutrino components that we have discussed, for instance, in matter or in vacuum, and characterized by two terms corresponding to neutrino oscillation in vacuum and matter. It's just notation that it's different, but a new term. Now, all these equations can be written, but I didn't do that, with the help of a vector. Actually, one vector for every energy. So the thing that it is that you can express the density matrix as a superposition in the two-dimensional case of the identity plus the Pauli matrices. And the coefficients are the component of this vector that is called polarization vector. So neutrino oscillation, even in the simplest vacuum case, can be described in the formalism that we have discussed until now, with the amplitudes and probability as we have shown, with the density matrix, and in terms of these polarization vectors, that is immediately equivalent to density matrix. But the density matrix approach is needed here because of this term. R is the distance from the center of the exploding star, the neutron star. P is the momentum of a neutrino, let's say. T is the time. And you see here that you have a non-linear term, because this integral depends on the neutrino we are considering, the propagation direction of a neutrino, the radius, but also on the rho for all the directions, q. So there is this integral, and more specifically, depends on the direction, relative directions of two neutrinos. So imagine that two neutrinos are scattering. This depends on the relative scattering angle between the two neutrinos. Now, you have to study this differential equation up there, and since it depends on the momentum, so on the energy of neutrinos, typically if you have the spectrum from a simulation, you take discrete values for the energy, and you get a series of differential equations, non-linear, because you have also this term, and you have to solve. And typically you have to solve thousands of differential equations to solve this problem. What is happening is that neutrino-neutrino interactions, since the density is so high, okay, I will introduce then another quantity. Because of this interaction, neutrino form approximately a sphere, neutrino sphere. But from the surface of this sphere, where neutrino are trapped, flux are emitted, let's say in the first approximation, half isotropically. Okay, go outside with some symmetry. But after, let's see, so the radius of a neutrino sphere is typically of the order of 10 kilometers or so. Actually, you have more than one neutrino sphere, because interactions are slightly different for neutrinos, antineutrinos, the cross-section differs. But in the first approximation, you can have one sphere where neutrinos are trapped, and from, take this direction for instance, from every point of this surface, the flux are emitted in all directions, and you can have, for instance, this neutrino propagating in direction p, scattering here at a certain distance r, with a neutrino with direction q. And this is what you have to calculate here. Okay. This simple model was called bulb model. Okay. And this was a particularly symmetric model because you have a sphere, you have isotropic emission of neutrinos in half the space here. And so it was relatively simple to deal with. And it was realized by Georg Raffelt, that all this problem can be rewritten as the equation of motion for a spherical pendulum. It is a bit strange that this formalism corresponds to the motion of a spherical pendulum, okay? And typically, by studying the equation for this pendulum, you can identify three regimes. Now, let me introduce one more quantity. The vacuum oscillation are described by, as we have seen, delta m squared divided to E. This is what appears inside the oscillation probability. Let's define the frequency in this way. 1 delta m squared because we are considering the simplest two-generation case. Then we have the matter potential, square root of 2 GF and E of R. This is also a frequency, so we can compare the two. When these two frequencies are of the same order, matter effects are important. But we can also introduce another frequency in the problem, the square root of 2 GF, related to interaction, the neutrino plus antineutrino density. Okay? This is, as you see, this has the same dimension, so it is a frequency too. And you can plot these quantities. Okay, this is what the bulb model, no, that I... And if you plot as a function of the radius the self-interaction potential, mu, and the matter potential lambda, you see that a small r, so less than 30, 40 kilometers, this depends on the supernova model that you consider, mu is higher than the lambda, so it must have some effects, okay? And by analytically, you can do a series of, you can study the problem quite well in the case of the bulb model in two generations. And you can identify three regimes that we call synchronized oscillation, bipolar oscillations, and split. Now, what are synchronized oscillations? As I told you, you can expand the raw matrix. Okay, it was something like 1 plus P dot sigma. Okay, if I remember well. So you have the coefficients of the Pauli matrices that form a vector, P. And you can write the equation of motion for the density matrix as equation on these vectors here. So we think of rotating vectors, these polarization vectors. Now, you have one vector for every P, okay? So every energy. Actually, you have an infinite number of vectors. But if you discretize the energy, let's say you have for every energy, one polarization vector. In particular, the oscillation probability that is related to the non-diagonal terms, off-diagonal terms of the density matrix, is related to the third component of this vector, okay? It can be shown that the oscillation probability, for instance, in the case of two flavors, E and mu, PEE will depend on P3. Okay, so the third component of this vector, and you have to calculate how this vector rotates. This vector can also shrink and now in the first regime, where the self-interaction potential is very high, it is like that all polarization vectors rotate with the same frequency. So the oscillations are synchronized. If oscillation of these vectors are not synchronized, the effect is a change in the spectrum, because every polarization vector has fixed energy, allows to calculate the survival electron nu E probability. If these are different at different energy, this means that the spectrum is changing. After this regime, actually this frequency, this radius can be calculated fairly good, well with the pendulum approximation. If you take the sum of all these polarization vectors that initially were rotating with the same frequency, now they start, their integral, that is the pendulum, starts to fall down. Boom. By considering all the initial conditions, it's like the pendulum is starting up, okay, and rotates like this. All the polarization vectors rotate the same way. After a while, when mu decreases, the pendulum goes down and starts to rotate around its equilibrium position. This corresponds to these polarization vectors oscillating, okay? And since mu is changing, it's like the potential in which the pendulum is moving is changing. And the pendulum tends to stop in the downward position. And here, after around 100 kilometers, splits of the spectra start to manifest. What are these splits? As I told you, there is a kind of hierarchy in many models for the supernova neutrino fluxes. For instance, if you make plot as a function of the neutrino energy, energy is in MeV for supernova neutrinos, and in arbitrary units you write the spectra. Typically you have the neutrino like this, nu E, and nu X like this. So the absolute flux is larger than for nu E than for nu X, but the mean energy is lower for nu E than nu X. And for antineutrinos, you have to write a similar equation for the density matrix, okay, but with some sign changing. You have a smaller flux. Let's say this is for antineutrinos, and you have nu E and nu X. Okay, actually these two should be equal. Okay, so the scale is wrong. I will show the picture in the plot. And this is the initial condition, okay? Now look at the upper plots where it says single angle. What is single angle? You should study this equation for the density matrix, but this is very difficult. The first approximation you do, you take an average over these angles here. And if you take the average, this corresponds to the case where the emission angle, let's say this one, is pi over 4 always. Obviously, this is not possible, okay? But you are, in some approximate way, averaging this term here. And this is the single angle approximation. Now, you don't see the initial spectra because these are the dotted lines, these ones, okay? What you observe is that after synchronization, bipolar oscillation, in the final part of the pendulum motion, you see there is some energy here around, in this case was around 7 MeV, here, so that what was, imagine you are at 100 kilometers, so 150 kilometers. So you started with this new E flux, and then you look at 150 kilometers, what happens? You see that at this energy, what was the new E spectra is this one, and then goes over the new X. There is a swap of the spectra above this 7 MeV, in this case, okay? And the opposite for the new X, that, okay, the dotted line, the lower dotted line, now this new X, it is difficult to see on this plot, goes over the new E spectra, and then back to the initial one. So this strange phenomenon, this that we call split and swaps, okay? For the antineutrino spectra, there is a near complete swap. So the new X, new bar X, goes over the new E, new bar E, and vice versa, with the exception of a small part at lower energy. You see there, okay? Now, this strange behavior more or less can be explained pendulum analogy, okay? So you can find an estimate for, where synchronized oscillation ends, where bipolar and how bipolar oscillation develop, and what is the energy where the split of the neutrino spectra happens, okay? This fact happens in inverted ordering, if you consider two generations, not in normal ordering. So it was believed, okay, if we see something like this, this would be a clear indication of inverted ordering mass spectrum. So we were very excited about these findings. There is more. From the point of view of people working on numerical evolution, explosions of supernova, since you have that, because of this mean energy hierarchy, part of the new E electrons will have a mean energy higher after the split. This could help the explosion, because more energy could be transferred to the shock for a revival of the explosion. First thing that we thought, okay, let's see what happened if we, from this single angle approximation, we go to the full solution of this problem. Full solution in the case of the bulb model, so with symmetry. And we found, this is called multi-angle, so we take into account this factor here. What happens is that, okay, the split is still there, but there is some smearing of the features. Okay, so you still find that there is the swaps of the spectra. But the fact that now you have this angular dependence on the equations, makes things a bit... okay, fine, this was the picture, let's say, 15 years ago. Then, okay, instead of considering the two neutrinos, so two generations, you can consider 3 generations. And as you consider 3 generations, you see that something similar can happen also for normal ordering. So it is no more a question of the inverted ordering, but also in normal ordering you can have splits and swaps. And things get more complicated. You can have 2 splits. For instance, you can have something like for the new E. Imagine this is the initial spectrum. The other one, this is new X. You have now 2 energies. Okay, something like this. And these 2 energies depend on the luminosity, total luminosity of the neutrino fluxes in nu mu, nu tau, and nu e. So we started to study this structure in a triangle with the luminosity. No? The total luminosity is fixed from the supernova you are considering, but how they are distributed in different flavors can change, and this structure depends on, and this is true also for normal ordering. But then, if you start to introduce perturbations means the emission is not half isotropical. Actually, 3D simulation tells you that the emission is not isotropical. Or the geometry is not exactly spherical. Every time it seems to, this is what was found. Every time you consider some small perturbation, all these patterns tends to be washed out, disappear. And what can happen is that you have completely, we say decoherence, meaning that all probability go to 1/2, and in the end you find that the spectra of all flavors are equal. And if the spectra are equal, oscillation will be ineffective. So the problem at a certain point was to understand if perturbations of the simple bulb models, let's say, destroyed these split swap patterns. Okay, and this was what seems to happen. But there was another complication a few years ago, because these oscillations, as we have seen, the bipolar, synchronized bipolar and then split, have happened on a scale of tens of kilometers, 100 kilometers. But there is another kind of oscillation that is called that are called fast oscillation that can happen on a scale of few meters and then can equalize the spectra. But before saying something about this, to study if there is equalization of spectra, typically one takes the equation of motion, and makes a linear stability analysis. So linearizes the problem and then makes, okay, I did something. Stop share. Okay, no problem. And one try to find if there is an instability or not. Instability about these vectors means that in the end the oscillation probability goes to 1/2. Okay, so it's a bit strange to say instability. Instability is when something grows exponentially, but you are doing a linear stability analysis. So when something grows, then the approximation of linearity is not true anymore. Now, there are oscillations of the kind, let me see, of this kind. Let's say nu E P plus nu X Q going into nu X P plus nu E Q. So imagine nu E and nu X exchange their momentum. Okay, there are others also. Now, it was realized through a stability analysis that if in angle there is a crossing between the spectra of, for instance, nu E and nu X, the instability related to this kind of interaction is there, and the fast oscillation on a scale of 1 meter will cause complete equalization of the spectra. Complete equalization is not exactly true because the lepton number is conserved. So you cannot have complete equalization of spectra. And the problem of, when I say crossing of the spectra, if you make a plot of the spectrum as a function of the angle for nu E and nu X, there should be a crossing. So at some point, one spectra is larger than the other and then lower than the other. If there is this crossing, there are these fast oscillations, and fast oscillation before the synchronized oscillations can make the spectra nearly equal. And if the spectra are nearly equal, there is no split, swap, whatever. And if they are nearly equal, there is no MSW effect after at 1,000 kilometers. So we are now in a very strange position because we have realized that there are at least 3 different mechanisms operating. The usual MSW oscillation, okay, but what are the initial spectra for the MSW effect? Okay, it would be this one, for instance, because this one is the spectra, these ones are the spectra at 200 kilometers. And these are the inputs for the MSW propagation. But the inputs for this collective oscillation, these were called collective oscillation, are the one emitted at the neutrino sphere. But at the neutrino sphere, near the surface, fast oscillation can happen. And if there are fast oscillations, these two spectra up there, the dotted one, would be nearly equal. If they are equal, there is no swap or split. And if there is no swap or split and they are equal, the MSW effect also will be ineffective. So supernova neutrinos are very interesting at the moment, and the study of the complete equation, also with collisional term, is an open issue, very difficult numerically to do, very difficult, because you have nonlinear equation, also integral differential equation to solve, and there is still another complication that we overlooked completely. This should be done together with the supernova evolution, because the supernova explosion depends on the neutrinos, on what neutrinos do. Now, there have been very recently some effort to put oscillations, fast oscillation, inside the numerical simulation for the supernova in some effective way. So the problem is complicated in many senses. And when your supernova will explode, maybe the spectra, the observed spectra, will tell us something, okay? And we could do the opposite. Instead of using models to study neutrino properties, from experimental spectra, we could infer what is happening at the neutrino sphere. Who knows? Okay. And so, I don't know if there is someone among you that is studying supernova neutrino. This is a very interesting problem, but a very complicated one also. And I think that I'm done. And I thank you for your attention. Okay.